So at the end of last class, we were just kind of speeding right along through linear algebra, and we came to the determinant. So this is going to be really important when we want to find eigenvalues and eigenvectors, which we'll do by the end of today. When we have larger than 2 by 2 matrices, to find the determinant, we need a couple other pieces of nomenclature. So we can remove one row and one column of our determinant. And we have now a determinant of order instead of n. Now we have a determinant of order n minus 1. And we call the new determinant so minus 1 row, minus 1 column. We call it the minor, M-I-J. So if we take an example, we have this 3 by 3 matrix. The minor of, let's identify A23. So the minor of A23 is going to be the determinant that's left of after I cross out row 2 and column 3. So M23 equals 1 minus 5, 2, 1. There's something called the signed minor. And the signed minor is -1 raised to the I plus j. So it's the sign of the minor, essentially. And we call this thing the cofactor of Aij. So in this matrix that I have here as my example, the element 4, the A23 element, is in row 2 and column 3. And so I plus j is equal to 5. And so the cofactor of 4 is -1 raised to the 5 times M23, which is just -11. So it's really convenient when you're starting to run through these determinant problems to get the proper sign for your factor, to think of a little checkerboard of pluses and minuses. So plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, etc. That's always going to be the sign on your cofactor for your element Aij. So if I labeled each of these entries in my determinant here, that would be the sign on the cofactor. Okay, so now that we have that language, cofactors and minors, we can easily say how to determine the value of a determinant. We just multiply each element of one row or one column by the cofactor, and we add the results. What's cool about this is that we get the same answer whichever row and whichever column we use, which is crazy to me, but math is neat. So let's just do a quick example with this same matrix that I wrote down on the last slide. So we have this 3 by 3 matrix. We can evaluate the determinant here using the elements of the third column. So let's go ahead and do that. So this is just equal to 2 times 7, 3, 2, 1, minus 4 times 1, -5, 2, 1, plus 5 times 1, 7, -5, 3. So then you can go through and do your 2 by 2 determinants. That's easy to do. And you'll end up with 148. And you can go ahead and check that if you did the same exercise with column 1 instead of column 3, you'll get exactly the same thing. So if we did column 1 instead, we would get 1 times 3, 4, 1, 5, plus 5 times 7, 4, 2, 5. Oops. Plus 2 times 7, 3, 2, 1. There we go. And that's also equal to 148. All right, so there's lots of useful things to know about determinants. So if each element of one row or one column of a determinant is multiplied by a number, we'll call it k, then the value of the determinant is also multiplied by k. The value of a determinant is 0 if all of the elements of one row or one column are 0, or if 2 rows or 2 columns are identical, or if 2 rows or 2 columns are proportional. If 2 rows or 2 columns of a determinant are interchanged, the value of the determinant changes sign, but not value. The value of the determinant is unchanged if the rows are written as columns and the columns are written as rows, so it doesn't matter. That's why it doesn't matter which ones we use. And we can add, the value of the determinant is unchanged if we add each element of one row to each element of one row, k times the corresponding element of another row, where k is, again, just any number. Okay, so that's cool, determinants. The other simple mathematical operations of matrices we're just going to run through really fast because we will need them, but you're probably pretty familiar with them. So let's just emphasize the fact that if we have 2 matrices, they're equal only if they are identical. So if I have this matrix equation shown here, it's really just a set of 6 equations. X equals 2, y equals 3, r equals 1, s equals negative 7i, u equals negative 5, v equals 1 minus I. And so in complicated problems, it's really useful when we have many numbers and variables to save a lot of time by just using a single matrix equation to replace a whole set of ordinary equations. So that's the goal. So if we have, if we want to display the components of a vector, our vector here is a equals 2i plus 3j, then we just write them as elements of a matrix. So we have the matrix A, which is just a column matrix, 2, 3, and the transpose of A, like we discussed last time, is just the row matrix, 2, 3. Okay, so if we want to multiply by a scalar, it's really simple in matrix mathematics. So 2 times A is just 2 times the entries in A. So that's generalized here. And I guess one thing to note is that it's a little bit different than what I just told you about determinants. So the difference between determinants and matrices is multiplying a matrix by a number k means multiplying every element by k, just like I'm showing here, but multiplying just one row of a determinant by k multiplies the determinant by k. So it's not the same. So determinant of ka is equal to k squared times determinant a for a 2 by 2 matrix, and k to the 3rd power for a 3 by 3 matrix, etc. Okay, what about addition? So when we add vectors algebraically, we add them by components. Matrices are added in exactly the same way. We add the corresponding elements of the matrices. So if I have these 2 matrices up here in the upper left, I just add the individual components like is shown in the top right, and that gives me the new matrix 3, 2, 2, 7, 0, 1. If we add A plus A, so if we just add a matrix to itself, that should get me 2A, and so that is consistent with what I just told you about multiplying matrices by a scalar. All right, so what about if we have 2 matrices that don't have the same dimensions? So like A and B here. What happens then? Can we add them? We can't add them. So we say that the sum is undefined or meaningless. All right, so in applications, matrices are useful in representing things that are added by components. So, for example, if in this matrix addition problem up here, I say that the columns represent displacements of 3 particles. The first particle is displaced by I plus 4j, so the first column of the first matrix, and then later it's displaced by 2i plus 3j, the first column of the second matrix. So the total displacement of that particle is just 3i plus 7j. So that's the first column of the sum matrix. So similarly, the second and third columns might be displacements of 2 different particles. So it's kind of handy, right? And it's pretty intuitive. All right, multiplying matrices. We got to start here by defining the product of 2 matrices, and then we'll see kind of what to make of this process. So here's a simple example, A, B, 2 2x2 matrices. The product of these 2 matrices is written out here. So the product of A, B, C, D with E, F, G, H is AE plus BG, AF plus BH, CE plus DG, CF plus DH. And that's our new matrix C. And we also call this product an inner product. And that's going to be distinguished from outer products later on. What we see when we kind of look at this equation is that the product matrix C, the element in the first row and the first column is obtained by multiplying each element of the first row in A times the corresponding element of the first column in B, and then adding the results. So we often refer to this process as a row times column process. So that's an easy way to remember what you do for inner products. And when we generalize this, we say that the element in row I and column J of the product matrix AB is equal to row I of A times column J of B. And if we wanted to write that in index notation, it's shown here. So it's the sum over K of A little I sub K, B little k sub J. So a useful way of saying this, we think of the elements in a row or a column of a matrix as components of a vector. And then the row times the column multiplication that we just did for the matrix product AB is the same as finding the dot product of row vector A and column vector B. So that's kind of if you're used to doing dot products with vectors, that's kind of that's the analogy. All right. So when we think about the product AB in that order, it can be found if and only if the number of elements in a row of A equals the number of elements in a column of B, okay? And when that is true, we say that the matrices A and B are conformable. And this is distinct, so we're not saying that the number of rows in A and the number of columns in B have to be the same. We're saying the number of elements have to be the same. Okay? And we can generalize this really easily to n dimensions. So the inner product of A and B across an n-dimensional matrix with over n dimensions is just the sum from I equals 1 to n of A sub I times B sub I. All right, so now that we know something about multiplying matrices, we can look at 2 other kind of useful properties of matrices, their length, and how to determine whether 2 matrices are orthogonal. So the length of a vector in n dimensions, we also call the norm. It's often written with these two lines with the matrix in the middle. It's equal to the square root of the product of, or of the matrix times itself. So if we write that kind of generally, we have, it's the square root from, of the sum of from I equals 1 to n of a squared. All right, and then we say that two vectors are orthogonal, so perpendicular. That means their scalar product has to be AB cosine pi over 2, which is 0. So we can generalize this also to n dimensions. We say that A and B are orthogonal if the sum over from little I equals 1 to n of AI, BI equals 0. All right, so in applications in quantum, it's useful to allow vector components to be complex. And so we want to ask ourselves, what needs to change about those three kind of general statements that we made about matrix multiplication if our matrices are complex and not real. So this is from Boaz. So she likes to use stars for conjugates instead of the lines. We've been using lines, so there's your lines. You'll see that physicists like lines and mathematicians like stars. Who knows why? Okay, so if we want to generalize these for complex matrices, we say that the inner product of A and B is equal to the sum over n of the conjugate of A times B. And the norm of A is equal to the square root of the sum over n of the conjugate of A with itself. And A and B are orthogonal if the conjugate of A and B summed over n is equal to 0. I feel like there was something I wanted to say here in addition. So yeah, the reason for this is because when we think about the length of our vector in a complex plane, so we saw this equation, so the sum over n of AI squared, right? We want that value to be positive because it's a length. So this is sort of why we have to revise our equations when we're dealing with complex numbers to involve the conjugate. Yeah, so we say that the absolute square of AI is equal to the conjugate of AI times itself. And so we're always going to replace the product of two matrices by the product of the conjugate of matrix A with matrix B. All right, so where does this bring us? In quantum information, we're going to be using brackets a lot, and we are going to write something like A, B in brackets to mean, and this is going to mean the inner product of A and B. So we're going to see nomenclature like this a lot, and next week when we run through the postulates of quantum mechanics, this is the nomenclature we're going to use. So we have the inner product of A and B. And what this is the vector space defined by this inner product, and we call it an inner product space. And this is true. We define an inner product space in this way if these things are true. If the inner product of A, the conjugate of AB, line, is equal to the inner product of BA. And if the inner product of A with itself is greater than or equal to 0, then the inner product and the inner product of A with itself is equal to 0 only if A is also equal to 0. The other things are less important, but also have to be true. And so when we talk about quantum mechanics and quantum information, you're going to hear the term Hilbert space a lot. And in finite dimensional complex vector spaces that come up in quantum information, a Hilbert space is exactly the same thing as an inner product space. So when we have a finite dimensional complex vector space, that's going to be called a Hilbert space. So don't get freaked out. It's pretty straightforward. So Hilbert spaces for us are going to be equal to inner product spaces. And they're named after this mathematician, David Hilbert. And we kind of can fully generalize this and say that they can have infinite dimensions and they will use other norms. And there's lots of different spaces that are defined in the context of quantum mechanics, broadly speaking, but we're only going to need a pretty specific set of them in this class that we'll go through over the next few weeks. All right, so kind of coming back around to something I told you last class, we mentioned that the adjoint of a complex matrix is its conjugate transpose, and we usually denote it by a dagger. And in either order, you take the complex conjugates of the entries and you transpose the matrix. And then we said that a Hermitian matrix is self-adjoint. So an n by n square matrix is Hermitian if it is equal to its adjoint or its conjugate transpose. Okay, so that brings us to unitary matrices. So if if U is a complex square matrix, then it is unitary if its adjoint is also its inverse. Okay. So what that allows us to write down is that U, a unitary matrix, times its adjoint is the same as its adjoint times itself, and both of those things equal identity. So this means that if the columns of this unitary matrix, are orthonormal to one another, and so are the rows. And what's cool is that the determinant of a unitary matrix is always equal to 1. So that's handy. And it turns out that all of the matrices that we're going to be working with, starting in a week or two, are unitary. So they're very simple, lovely matrices that have a lot of symmetry and easy to work with properties. All right, remember adjoint, conjugate, transpose. I feel like, for me, a big barrier to getting into this is just the nomenclature, and so I like just constantly remind myself, what does this mean? So you should get used to doing that too. When you see this word Hermitian, remind yourself what that means. When you see the word unitary, remind yourself what that means. And it will begin to become a little bit more familiar. Okay, so we've got to talk about eigenvectors and eigenvalues. That's kind of the last big concept that we need to review in math of quantum stuff, or to get us into quantum stuff. And so it's useful before we get into this to talk a little bit about diagonal matrices. So a diagonal matrix has zeros everywhere except on the main diagonal. So this example in the upper left, that's a diagonal matrix. It's easy to visualize what this diagonal matrix does to the standard basis vectors, for example. So the effect of this particular matrix on the standard basis vectors are to stretch it by a factor of 3 along the first, leave the second alone, and then reflect it across the xy plane, and then stretch by a factor of 2 along the third. So that's what you're doing by just having numbers on the diagonal. Okay. So a general diagonal matrix looks like this one that I have drawn in the bottom left here. That's a really big one. We are probably going to be dealing with much smaller ones that have less zeros. But there's lots of cool properties about diagonal matrices. For example, the determinant of a diagonal matrix is just the product of the diagonal elements. And the trace of a diagonal matrix is just the sum of the diagonal elements. And the transpose of a diagonal matrix is just itself. And we can invert diagonal matrices when none of the diagonal elements are 0. And if it is invertible, meaning none of the diagonal elements are 0, then the inverse matrix is just the new diagonal matrix where the elements are 1 over themselves. So diagonal matrices are great. We're going to work with a lot of them. If we are considering a basis B1 to Bn, then we say that the diagonal matrix times the basis vector 1 is just equal to the diagonal element 1 times the basis vector 1, etc. So if we look at this last effect of on the basis vectors, then if we start thinking about a general and not necessarily diagonal square matrix A, we can ask ourselves, is there a vector v and a scalar lambda such that AV equals lambda v? So this is a kind of fun question to ask. We can re-ask it just to kind of make it a little bit clearer. We can say, does the linear transformation represented by A have the effect of stretching in the direction of V by lambda? That's what this question is saying, right? All right, so if we have a square matrix A, if there exists a non-zero vector v and a scalar lambda such that this is true, AV equals lambda v, then we call v the eigenvector, and we call lambda the eigenvalue. Named after German stuff. You sometimes see them called characteristic vectors or characteristic values, but most often they're eigenvectors and eigenvalues. All right, so how do we find eigenvectors and eigenvalues? Takes us back to the determinant. So if AV equals lambda v, then AV minus lambda v has to equal 0. Here, this 0, it's bolded, right? This is the vector of length n, the 0 vector. So matrix-wise, I can kind of express this in the following equation. So I have A, my matrix, minus scalar lambda times the n by n identity matrix times my vector equals 0. So this expression is a polynomial in the single variable lambda, and its roots are the eigenvalues of, the determinant is a polynomial in the single variable lambda, and its roots are the eigenvalues of A. All right, the eigenvalues of a diagonal matrix are just the diagonal entries, which makes them really easy to find, kind of trivial to find. But we can kind of start there and build up to more complex systems. The corresponding eigenvectors of this kind of diagonal matrix are the basis vectors. So let's look at a pretty trivial case. So here we have a diagonal matrix, 1, 0, 0, negative 1. And by inspection, we know that the eigenvalues are, for eigenvector E1, is 1, and the eigenvalue for eigenvector E2 is negative 1. So we just read those off the diagonal. But we can go ahead and do the computation via determinants just so that we can get some practice. So what we would do is we would write out the equation. So we have the determinant of the matrix 1, 0, 0, negative 1 minus lambda times the identity matrix 1, 0, 0, 1 is equal to 0. That's what we need to get. Let's go ahead and multiply this out. So we have the determinant of 1 minus lambda, 0, 0, minus 1 minus lambda. You can go ahead and do the determinant, right? It's just 1 minus lambda times minus 1 minus lambda, which is equal to lambda squared minus 1. And if I go ahead and factor that out, I get that's equal to lambda plus 1 times lambda minus 1. This needs to be equal to 0. And so that gives me the answers to the roots of this equation. Lambda 1 is equal to 1, and lambda 2 is equal to minus 1. Okay. So what if we have something that's like a little bit more complicated than that? So what if we have this matrix, another 2 by 2 matrix? We're going to deal with a bunch of 2 by 2 matrices in our qubit systems. So we have 3, 3, 2, 4. So we generate the characteristic polynomial by using our determinant equation. So we have 3, 3, 2, 4 minus lambda times the identity matrix. So that's just equal to 3 minus lambda, 3, 2, 4 minus lambda. Lambda squared minus 7 lambda plus 6. You can go ahead and take time to factor that out. It's just lambda minus 6 times lambda minus 1. This needs to equal 0. So that tells us lambda 1 is equal to 6, and lambda 2 is equal to 1. So those are our eigenvalues for this relatively simple 2 by 2 matrix. Okay, so to find the eigenvectors for each eigenvalue, we have to solve the equation that we wrote down. So we have to solve 3 minus lambda times 3 3 minus lambda, the matrix 3 minus lambda, 3, 2, 4 minus lambda times xy equals 0, 0. So for lambda 1 equals 6, this is minus 3x plus 3y equals 0, and 2x minus 2y. And so either case just tells us that y equals x, and so we can choose any points along that line to represent the vector. So we can say, okay, v1 equals 1, 1. And then we can do the same thing for lambda 2. So that'll get us 2x plus 3y and 2x plus 3y. So that gives us y equals minus 2/3 x. So we can just choose v2 equals 1 minus 2/3. And then you can go through and verify that these make sense by plugging them back in. Okay, what if our eigenvalues aren't real? So we can look at this kind of final example here. It's a really simple little 2x2 matrix, 1, 1, minus 1, 1. And so we can generate the characteristic polynomial. I'm not going to write it all out because I already wrote it on my slide. So it's the determinant of 1, 1, minus 1, 1, minus lambda times the identity matrix. So that determinant equals lambda squared minus 2 lambda plus 2. So I can factor that out, and I get that lambda 1 is equal to 1 plus I, and lambda 2 equals 1 minus I. So that's kind of interesting that a simple little matrix like this doesn't have real eigenvalues, only complex ones. It kind of reinforces why we need complex numbers when we're going to start working with matrices. So we can, instead of working in the real plane, we can work in the complex plane, and then we proceed and find the eigenvectors just like we did in the last examples. Okay. So in the 2x2 cases, it's really easy to take determinants and factor the polynomials, and it gets much harder as the dimensions get higher. And people have developed fun algorithms and software to compute and estimate eigenvalues and eigenvectors. They're often called eigensolvers. Please use them. You'll have some gory determinant problems, and eigenvector, eigenvalue problems on your homework, just to go through the motions. But in practice, when you're dealing with bigger matrices, you're gonna not do them by hand. But we can let A be some complex n by n matrix in the complex plane. Then the polynomial, defined by the determinant of A minus lambda times the identity matrix, in the single variable lambda can always be factored completely over the complex plane. And so A has n eigenvalues and n corresponding eigenvectors. And some of those eigenvalues may appear more than once, and so we say that those values have a multiplicity greater than 1. And the determinant A is the product of n eigenvalues when we're talking about the determinant of A is the product of n eigenvalues, and the trace of A is the sum of them. All right, let's come back to diagonalizable matrices. So a matrix is diagonalizable if there exists an invertible matrix, we're calling it V here, such that the diagonal matrix D is equal to the inverse of V times A times V. So what this fun equation says is that there's a change of basis so that the transformation represented by A in the original basis can be represented by D in the new basis. And a complex matrix A is diagonalizable if all the eigenvalues are different. So it has all multiplicity of 1. It could be possible to diagonalize a complex matrix with repeated eigenvalues, but that's not true in general. If we can compute all the eigenvalues of a complex matrix, can we diagonalize it? The answer is no. We can only diagonalize it if all the eigenvalues are different. Okay, if A is a complex n by n Hermitian matrix, then all of the eigenvalues of A are real. The eigenvectors corresponding to the different eigenvalues are orthogonal. And we can always find a basis in the complex plane consisting of eigenvectors of A. And since we can always normalize eigenvectors, we can make this basis orthonormal, which is handy. All right, back to unitary matrices. So since unitary matrices are so important for quantum computing, they have special properties regarding being transformed to diagonal matrices. All right, so we talked about it a little bit already, but a unitary matrix is a square matrix of complex numbers whose inverse is equal to its conjugate transpose or its adjoint. So if I take the product of a unitary matrix and its conjugate transpose, that gives me identity. So if U is a complex unitary matrix, then we can say that there exists another unitary matrix V and a unitary diagonal matrix D, so that U equals the adjoint of V times D times V. And since the adjoint is equal to the inverse, because it's unitary, this means that V times U times its adjoint is equal to the diagonal matrix. So this is saying that there's a unitary change of basis for a unitary transformation so that it can be represented by a diagonal matrix, which is handy because of all these useful properties of diagonal matrices that we talked about earlier.